Dear students, today we are going to learn a new topic in quantum mechanics, that is quantum dynamics. So here we will be learning about time evolution operators and then many other features based on that. Now, before going into understanding what time evolution operator is, we have to keep in mind that in quantum mechanics, position is an operator, because we know that an operator acting on an eigen on a vector state, it can give position values as the position as its eigenvalues, right? But so which means that position is an operator, but then time is not an operator. Time is only a parameter, which means that no operator gives eigenvalue as time, which means that time is not an operator, but it's only a parameter. So in quantum mechanics, or the non-relativistic quantum mechanics which we have learned so far, both position and time are not considered in a same way, because one is considered as an operator and other one as a parameter. But in relativistic quantum mechanics, which you'll be learning in the next semester, both of them are considered to be different, because for the relativistic quantum mechanics, both position as well as momentum, they both are not operators, but they are considered as parameters there. So just keep in mind that time is not an operator, but then position is an operator in quantum mechanics. We come to the understanding of time evolution operator. Now, now you consider an eigenstate, say ket alpha, okay, at a time say t0, and so we write it as time ket alpha at the time t0. Okay, so this is basically the ket alpha which you always write. So that is basically ket alpha which you always write. So I think you couldn't see that. That is you can write ket alpha which you always write. That can also be written as ket alpha comma t0, which means that this is the state of the ket alpha at time t0. Now you consider at a later time, say at time t, at a later time, say time t. So this is at the time t0. You can write ket alpha as, it can be represented as ket alpha t0 t, where t is the time now and t0 is the initial time. So ket alpha t0 t represents the state of the ket alpha at a later time, say t. Okay, hope you understood. So this you consider as t greater than, where t is greater than t0. Okay, and this you consider as equation number 1. Now moving on to the next concept, that is, we can say that now since time is a continuous parameter, okay, since time is a continuous parameter, I can write this as limit t tending to t0, okay, then ket alpha t0 t. This can be written as time t tends to t0, what will be this one? That is initial time, right? So that is at the time t tending to t0 means it is the initial state. So then it will tend towards ket alpha, right? Is this okay? So which means that you can consider this as in a different way. That is, so ket alpha you can consider ket alpha t0 on time evolution, okay, becomes ket alpha t0 t. That is, as time changes, ket alpha t0 changes to ket alpha t0 t. Okay. So this is how ket changes. So it is as a case of a position translation or something, when we, or you can say that it is operate. So it can also be looked in a different way, that is alpha t0 t, and when it is being operated by something, which changes its state to ket alpha t0. So that is, you can consider this operator which changes its state from this to this is called as the time evolution operator, and you consider that it is written as you represent this time evolution operator as u t0, which changes its state from the time t0 to t. That is, I can write it as ket alpha t0 t equal to u t0 ket alpha t0. Okay, let me consider this as equation number 2. So this is the time evolution operator. Hope you understood what time evolution operator is. It is an operator which changes ket alpha t0, which is its initial state, to another state at the time t. Okay. Now we have to learn about certain features of this time evolution operator. And the first feature we'll be learning is its conservation of probability. Conservation of probability, or this can also be this property can also be written as unitarity of this operator. Unitarity of the time evolution of the operator. That is basically time evolution operator. Okay. Now, you know that any state can be represented in terms of an eigenkets, right? That is, we have written, that is, for example, I can write ket alpha as ket alpha is equal to, say, c1 ket a1 plus c2 ket a2, like that.